Hey everyone, I'm Max. Let's learn how to tackle this educator problem, continuous subarray sum. So this is, I dare say, the first problem in this series that does require a little bit of out-of-the-box thinking. That isn't just, implementation or straightforward usage of a data structure. And it's almost like a double abstraction from where you start to getting the correct answer. Um, but yeah, with all that said, let's talk about it. So in this problem, you're given an array of integers. This problem does not list constraints, but I will be talking about this as we go along. So these integers can in fact be negative. So they're all integers, right? You can have -1 or 1, as you can see in this input here, or obviously any negative or positive value. You're also given a target value, and we want to find the number of non-empty continuous subarrays. So what does that mean? Here we have 1, 1, -1, and 1, and we want to find the number that equal 1. Well, we could have just this one, or just this one, or we could have these two and these two. The important thing is that none of them are empty, so that if it was like 4, 0, we need to have like, or actually, no, sorry, that's my bad. It should be this one here, and this one that equal 1. I was thinking of 0. If we had 4, 0 here, we would actually like choose this one and this one. We couldn't choose any subarrays with no elements, and also all of the subarrays have to be the elements in the subarrays have to be continuous. So again, looking for 0, you can't choose this -1 and then this 1. They all have to be together in essentially a line, a continuous block. So again, there's our walkthrough for the sample output, right? We can get 1 by adding these three, or just taking any of the ones by themselves. Another thing, yeah, like I said, k can in fact equal 0. That's what we walked through here, and it should be non-empty. So our solution we might need to be a little bit careful so that we address that. So, just, talking through this, if the array was made of only positive numbers, I think one of the ideas you might jump onto is something called like a sliding window, right? Where you essentially have this window. Say our target is 3, right? Where we have this window that expands and contracts to get elements. So here we would say, okay, the window first encompasses this 1, and 1 is obviously smaller than 3, so we'll add more elements into the window. We'll add this 1, still too small. Now it's at 4 when we add another element, so we'll drop this 1, and now we have 3 within this window here. So we've kind of accomplished our goal there of finding that 3. And that works when we have only positive elements. But here again, we can have negative integers, which kind of complicates things, right? It's not always guaranteed that selecting or broadening your window is going to give you a higher number, and contracting your window is going to give you a smaller number. It's just more complicated than that. And here we want a solution that runs in O of n time. So it's pretty difficult to look through all of our different subarrays and think about which ones could equal to target. Now, that's ultimately what we're trying to do here, right? Essentially, look through all of the subarrays. Now, putting aside that O of n, would there possibly be a way to look through every single subarray in a fairly simple or efficient manner? Let's pull this up real quick. Um, let's say I want you to think about the subarrays that end with this last element, right? It would be this element here, or this here, then this, then this, then this, right? And then what you could do is you could go to this element here, which obviously is just that element, then all of these, then all of these. And that would represent all of the different subarrays. But note that when I take a subarray here, what I really care about is the sum, right? The sum of that subarray. And one thing that isn't really impacted by the presence of negative numbers is the fact that if we have the sum of, say we want to get the sum of just this subarray, which we know is 1. If we have the sum of this entire subarray, again, that's 3, and subtract this, we would get that last subarray, right? So here, the 3 minus the 2 would give us the 1. And so we can almost perform these different operations to get every possible subarray. So what ends up happening is that we don't need to calculate every single possible subarray, but rather every possible subarray that starts at the start of the graph or at the start of the array and ends at any point. So why is that? Say I have the sum of this entire, all 4 elements, then these 3 elements, then these 2 elements, and just this element. You can convince yourself that you can, in fact, find any subarray with just these 4 numbers. If I want to find, say, this, well, all I have to do is take the sum of the 3 elements, 2, and then subtract this sum, right? Which will give me just these values, these middle 2 values. So the 2 minus the 1 will give us 0. Or sorry, the 1 minus the 1 will give us 0. Let's try a different one. So say I wanted to get this one here. Well, I would take all 4 numbers, the sum of all 4 numbers, which is 3, which is 2, Jesus, and then subtract the sum of the first 2 numbers, which is 2. Again, that leaves me with this section here, which is 0. So hopefully we've garnered some intuition there that what we really care about is the sums ending at each number, the sums of the subarrays starting at the start of the array and ending at each number. Now, we can calculate this pretty easily, right? Because we can start with a sum of 0, add the first number, that's what we can store for our first sum, add the second number to what we already have cumulatively, store that as the second number, then add this third number to that cumulative sum, store that as the third, and so on and so forth. This is known as a prefix sum, and there's a few ways we can write this. I'll write it here, and we can actually overwrite the original array if we don't want to create any more space. So in this case, say we are keeping a running prefix sum. Fix the indentation here. We can iterate through the arrays. Int I equals 0, I is less than or size, plus plus. And for each element in the array, we add to the prefix the element at that array, so plus equals array I. And then we overwrite that element in the array to be the prefix. So let's use that method to calculate the prefix sum of these 4 numbers here. Here we start with 0, right? We make this, or we add that value to the prefix. So prefix becomes 1, and we set it to the prefix. So that's 1. Prefix is now 1. We'll move on to the next element. We add this element to the prefix. Prefix becomes 2, and we set that element to the prefix. Move on to the third element. Prefix is now 2. We add this element. It becomes 1 again, and we set that element to the prefix. And we move on to the last element, add that to the prefix, which is now 2, and store that in that array's location. We don't actually need like an external variable to do this. We can just be like, this value plus this value is this value, for every value in the array. But again, for simplicity's sake, I'll code it here with a prefix or with an external variable. Yeah, if you want, you could start iteration on like this first element, and again, just be like, oh, it's the last element in this array plus the current element that will give you the prefix, and then just do that for all of them. That works as well. But either way, we now have our prefix sum, which, as we said, we can use to get the sum of any contiguous subarray. So for instance, say I wanted to get subarrays of length 0, what I would do is, or what I could do is see that, okay, this whole, all 4 elements together have a length of 2, and these 2 first elements together have a sum of 2. So if I were to take the 4 elements represented by this number and the 2 elements represented by this number, if I subtract these 2 numbers, I get 0. That just indicates taking this as a subarray. So for something like a k equals 0, we'd want to find matching pairs, right? The 2 matches with this 2, and the 1 matches with this 1. Now, say we go back to the actual test case, right? Here, k equals 1. What we're looking for here is no longer matching pairs. Let's say we're at this last element, right? We know that everything up to this and including this element, if we sum it all together, it has a sum of 2. Well, our target value would, instead of being 2 itself, like it was in the last time, when the last time we were talking about k equals 0, it's now 1. Because if we find a 1 in this array, that basically indicates that all of these values sum up to 1, but that the elements that we add after that also sum up to another plus 1, right? So this element itself, or this subarray itself, will also sum up to 1. If we were at instead of being at a 2, say we were at a 1, so not at a 2, say we were at a 1. Here, what would be the target? Well, we're looking for 1, so we'd want to find a subarray with length 0 to stop at. So essentially, everything up to here is at 1, but if we have a subarray of a length 0, we can stop there because we would know that these equal to 1. Not the case in this, array, but our target here would be 0. We're looking for zeros. And as a whole, all it is it's the current element in the array minus this k value that will give us the target that we're looking for, where the full array minus the sum of that target indicates that this is our k. Effectively, we can kind of do some algebra, right? The full, which is like array at I, so it looks like a j, minus the partial, which is the array at the target, is equal to k. So if we want to find an array of target, that's just equal to array of I minus k. So that's array of target. Right? So that's good and all. We know what we're looking for, but we want to, again, do this in O of n time. So what we're effectively doing is at a certain value, say we're on this last element of the array, we know that here our target is 1 using this formula. So we want to find how many times this array has had 1s before this index. And again, that O of n squared solution, we can just look backwards, iterate backwards, right? This is a 1, this is a 2, this is a 1. And that would work, but that's a little slow. What we can do instead, I mean, come on, look at the units, sets and maps. While we're iterating through the array, we can store what value we're at. So essentially, say we're iterating forward through the array, right? We're at a 1, and we store that we've seen 1, 1. We're at a 2, we're at the 2, so we store that we've seen 1, 2. We go to this 1, now we've seen 2 1s. When we get to this 2, and we look for a target of 1, we know that we've already seen 2 1s. So we can just say, here or here is one of the subarrays, and here's one of the subarrays, right? It's equal to the amount of times we've seen target before. All right, let me erase all of that and transcribe that logic into code. Some cackling outside, sorry. What we're essentially going to be doing is iterating through this array once again. And what we want to do is first, let's just calculate a target using that formula we found before. So we'll say that our target value is equal to the value we're currently on minus k. Essentially, we have an array that has, or that from the beginning, from our current value to the beginning of the array, it has so much sum. And to get to the k, we need to cut out a certain target sum. And so the subarrays that also start at the beginning of the array, if we can determine which subarrays have that target sum, we'll be left with just a subsection that has that sum of k instead. Again, I really think you should draw this out with the prefix sums and whatnot, maybe write some sample test cases if you're confused here, because it's not super intuitive to wrap your head around the first time you see it. And here, let's say we'll make a variable to actually store what we're returning here. Here, what we'll return is, or we'll add to res the number of times we've seen the target before. And the way we can store this is using an unordered map, for instance. So this will just map integers, the sum values, to integers, the amount of times we've seen those values. We'll call this targets, maybe. Or you know what, maybe I'll call it sums. We already have a target variable. I don't want it to get confusing. So here, we'll add sums of target, the amount of times we've already seen that target value occur as a sum of the array. Now here, after this, we want to update the sums array. Sums of array I plus plus. Essentially saying that the current sum that's stored up to that I value, we've seen it, we will increment it. Now, why do we do this before this? Or sorry, why do we do this after this? Well, what if our target is equal to array I? What will happen? Well, what that represents is, say our target is 8. Or no, say our target is 0, right? And we're at a element 8. Here, 8 minus 0 makes target equal to the array value. And so we'd essentially be saying like, by adding this first, we'd be saying, okay, I want to have an array of, from the start of the array up to this value, with everything up to this value removed. So there's nothing in the array. That is the that is the empty contiguous subarray. I think it's a little easier if I put something before this 8 here, like a 6 or something. Again, we're at here, and we want to get zeros. This is what our current, or what array I stores. It's this whole sum here. And if we were to update it first, we'd essentially be able to catch this 8 and be like, okay, I want to know this. My brain's kind of fried, so I don't think that was a great explanation. I'll give it to you 100%. But basically, we do this to avoid counting those empty subarrays. We return this. So let's run this at our 0 test case and see what happens here. Let's see if educator works. I might have to refresh the page. Sometimes it just does that. I don't know why. Let's refresh the page. Maybe it has my work saved. Oops, okay, I guess we're running on 1. Now, notice the correct output is 5, but we only output 3. Why is that? Well, this is an error I've left into the code because I think the code is pretty, if you understand it, you understand it, right? There's not like a super obvious, I think, error that jumps out. Let's rewrite our prefix sum, right? Focus on the start of the iteration, right? At this first element. Obviously, this represents this behind the hood, and we want to give, this is obviously a correct array of length 1, or of sum 1. And yet, when we're at this 1, there's nothing in the map, right? The target, say, it's because the target here is 1. If we do array I minus the k would be 1. Sorry, the target would be 0. And yet, there's nothing in the map for that 0 to match to. And thus, we move on without adding anything to res. And this is a problem because, again, this is a correct subarray. We're missing that. And so the issue here is that we're never giving these prefixes the ability to cut nothing out of themselves. We can essentially say that before the first element of the array, there's a subarray with cumulative sum 0, right? And if they want, they can take that and cut everything before that out of their subarray, effectively nothing. And the current implementation doesn't allow them to actually start at the start of the array, to choose a target that is cutting out nothing. And so how we address this is we simply increment sums of 0, like so. Again, this 0 represents essentially taking that 0 before the start of the prefix sum array. It's cutting out nothing from your cumulative sum. You can see we now get 5. Let's run the code, and this should work. There's one more thing that I do want to say. I know this has been probably a very confusing video for a lot of people, but one thing I do want to note as well, notice that we're iterating over array twice. One time we are going forward and updating our prefix value, so that just, requires what we have at every, it's only dependent on the values behind it, every index we update. And then we also iterate through once to update res, to update the target, the sums array, and add to res. That is also only accessing or only important because of the it's only working based off of the elements behind I in the iteration. Because remember, sums will only ever be updated by the previous elements, not by anything ahead of the current element. And because of that, we can actually combine these two loops. Basically smush these both together. First, update the prefix, like so. And then using that prefix, calculate the target and obviously update that value. Using the prefix, calculate the target, store that target in the sums array, add that to res, all that good stuff. But essentially, since we're only ever using the elements previous to a current element, we can do these both at once. And that simplifies the code a little bit, like so. But I didn't think it was worth actually coding it like this because I think the logic is a bit clearer when we split the two steps. But it does simplify the code a little bit. All right, that was probably a bit of a long video. I have to start my discussion now. If you have any questions, reach out to a TA. If you have a question about this video, I'm TAing, you can talk to me about this problem if you'd like. With out of the way, I don't know, maybe this is the final problem in the sets unit that you're working on. If so, then I've already recorded the graph videos. Good luck with graphs. Otherwise, you've probably done maybe the hardest problem in the sets and maps problem set. So I'd say good luck on the rest, but you probably won't need it. Regardless, great work. I'll see you in the next video.